Our first keynote speaker requires maybe not too much introduction, but anyway, it's my great pleasure to introduce Brad Rothenberg. Brad studied architecture at the Pratt Institute in Brooklyn, and for the last 10 years has been developing computational design tools for advanced manufacturing. Brad is the founder and CEO of nTopology, which is a company based in New York that has received a lot of attention in recent years for doing some really revolutionary things when it comes to design and analysis tools for engineers. For instance, as I think we'll hear about today, they've been using Sine distance fields, or SDFs, as a first-class representation for geometry in engineering, which is pretty incredible and lets them do a lot of things you couldn't traditionally do. And I should also say that nTopology has been a big supporter of research and researchers from the geometry processing and the graphics community. So we all very much appreciate that. And hopefully Brad's talk today will inspire us to all engage even more and think about geometry processing from a slightly different point of view than we normally do. So take it away.
Ian, thank you very much for the lovely introduction, and it was enjoyable to chat before this as well. As I was saying before, I'm in Portland right now traveling, so I apologize if the lighting and all that stuff and sound is okay. I see there's like a chat box also, but I'm not paying attention to it right now. But if somebody wants to ask a question while I'm talking, feel free to interrupt me. Maybe somebody who's on the moderating panel can just like jump in and interrupt me and stuff like that. Talk today is about engineering-driven design, a new foundation. As Keenan was saying, we built a new company on top of kind of new fundamentals. And so I'm going to talk about that stuff today. This is more of a business-focused presentation, not so much. I mean, you guys have probably been in academic talks for the last couple of days and the next couple of days. So this is more, what are, with all the research and stuff like that, what does the actual business side of this look like? And what are we actually doing in the world? And so the talk today is structured in a couple ways. Let me see, can I change slides? So to start with the new reality, like what's changed in the world? Why can we build new engineering software today? What are some of the problems that engineers are facing? How are we at nTop solving those problems? And then, where we're making an impact. What are the industries we're in? As I was saying before, medical is one of them. And then what are the challenges and unknowns that are still really big open areas of research, and there's a lot of hard stuff that we still need to solve to kind of successfully transform the engineering industry for the next generation. I mean, the goal is to, make computers the best engineering tool for the next generation of engineers and manufacturing. And so, what's changed today? Why are we bringing new engineering software to the market, right? The way that we make things has fundamentally shifted in the last 15 years. This is the, traditionally called the digitization of the factory. There's some kind of cheesy terms, industry 4.0, digital 4.0. Basically what this means is we're making things from the computer, thinking from the computer first, right? In the previous generation, CNC machines were programmed by people. There were drawings given to people. Things were cut out by hand. Today, the factory looks more like the way chips are produced almost. When we go around and go through some of our customer sites, these don't look like, your grandparents' machine shop or like the factories that you've seen in like history class. These look like chip production facilities, and these are digitally controlled machines. The issue is the design software was designed in the late 70s, early 80s, and that's now a bottleneck for engineers. It's a bottleneck because that software was built, mainly for drawing and drafting. CAD originally was architected to be a better drawing tool on the computer. It was meant to digitize drawing. It wasn't meant to digitize engineering. And so the goal with nTop is to be the best tool to use the computer to engineer better 3D parts. And that starts thinking from 3D first. Engineers can't do their job because of these bottlenecks. It's actually become a joke online. There's like thousands of memes. There's some memes that I had to pull from this because I thought they were inappropriate potentially. But I like this one because it's like, I have my crush on one side, I have Katia on the other. What's the similarity between the two of them? They both don't respond to me. And this is like a common joke, right? You make a change in a CAD program and you have to like get up, have a coffee, wait for it. Your whole model tree is updating. And then you come back and, maybe there's a model failure, maybe there's an issue. And so these bottlenecks actually are preventing engineers from doing their job and designing really high performance products. And so I started nTop with the goal of enabling engineering teams to, design the most transformative products. And we'll get back to this example before, but this is a Cobra Aero engine, lighter weight. It's 3D printed first. It's thought in 3D. It's controlling. It's a multi-physics. The engine has to, has air cooling the engine. There's a cylinder moving up and down, creating a lot of heat under a lot of pressure. Normally, these are cast out of aluminum. With 3D printing, they actually integrated the heat exchanger through it. And we'll get back to this a little bit later. But first, what are some of the problems faced by engineers, right? One, the modeling, the core is the modeling operations. The core issue to failures, to slowing down engineers' work is the fact that when you do something in CAD, it's unreliable, right? Whether booleans fail, shelling fails, filleting fails. These cause problems downstream. If you're trying to model like the tooling and molding for this glass bottle, right? And you're adding all the little fillets and rounds and stuff like that, and you make a change to the bottle because you're Perrier and you need to, make a bigger bottle for the American market, right? Like all of a sudden you make some changes to that mold and it fails and you have to spend a lot of time redesigning it. This fragile modeling has even bigger implications, right? If you want to design higher performance parts, a lot of engineering is trying to explore what's possible, explore the realm of what's possible and see if you can make it better, make it perform better. Maybe it's a mold that you're trying to make lighter. Maybe it's a bracket for an aircraft that you're trying to make lighter because you need that aircraft to fly and not just sit on the ground, right? You need to be able to explore. That means push on the model, change it, change the parameters, etc. If 50% of the time, if 80% of the time that you change those parameters and the model doesn't update, you're not going to be able to explore that design space or explore what's possible. And you're just going to run into error after error after error. And that, again, prevents you from making a better part or a more optimal product. Additionally, with things like 3D printing, we could produce these structures that were like impossible to make in the past. Structures that have the complexity, or are more complex than things that you find even in nature, the natural world. Things like bone implants that have to fuse with bone as you put a titanium plate in to have a, for a knee or hip implant. These models require a lot of geometry. They require these, these are like genus 1 billion, some of these structures, right? How do you actually represent that in the computer with, 1 billion holes in it? And so that's where nTop comes around, and I'll get into the modeling a little bit later, but with BREPs, the technology that drawing-based CAD is built upon, it doesn't scale well to these mega structures, right? And additionally, in drawing-based CAD, you have this pipeline where you have the tree structure in CAD, which actually is a procedural model. Then a BREP is calculated from that tree structure. It's then converted to facets, which are sent to the GPU and rendered as pixels on the screen. With the nTop model, we go straight from procedural to pixels, and we'll get into that a little bit. And so, how do we do that? Well, there's really 3 top level differentiators. Like, it starts with the modeling technology or the core model, right? Like, when trying to re-architect engineering software, we weren't like, okay, we're just going to build another hack on top of the BREP model to try and make it scale into this new generation of engineering. Instead, we're going to re-architect that, or look at what's a better architecture for building our modeling tech on top of. And that enables 2 really key areas: field-driven design and reusable workflows. Reusable workflows, the ability to change the model or reuse parts of one model somewhere else. Like, you want to apply this bubble pattern to something else, you can model it once and then change the parameters of the bubble and the model will just update, right? Field-driven design, it's actually taking the physics and the real world and using that real world information and data to drive the model parameters. And that's really important, as we'll see a little bit down the line. But starting with unbreakable geometry, again, rather than try and hack on top of BREPs, I see the chat box is like popping up. I don't know. Maybe I should monitor it. Let me see. Sorry.
We'll let you know.
Got it. Yeah, cool. Yeah, Keenan, just interrupt me if thanks. So this is, this term first principles. Well, again, rather than try and like hack on top of the BREP model to like make it work, and for these complex gigascale models, reliable modeling, etc., we wanted to see like, okay, let's just ask the first question. How do we use the computer to engineer parts better than nature, right? Like if I want to model this bone has a really interesting structure, right? There's more material where it's more where there's higher stresses, there's less material where there's less stresses. The material's put exactly where it needs to be. And again, a BREP model is probably not the best model for this, right? A BREP is a boundary. If I wanted to represent this with just the boundary, it would be crazy to try and calculate that boundary everywhere. Instead, we can start with Sine distance fields instead as the representation, and it's better for a number of reasons, right? Like, so again, if we think about the question, how can we use the computer to engineer parts better than nature, not just copying nature, but better than nature? It starts with using the computer to draw shapes in a more efficient way, in a better way, right? Compared to BREP. BREP, because it was based on trying to use the computer to make drawings, you only need the boundary for a drawing. When you see something, you draw it, you just draw the outside. You don't need all the information inside or all the information outside. If we're engineering, we need all of that. We need something closer or better than what actually gets made in the physical world, in the digital world, to capture the complexity, right? Because with the Sine distance field, and we call it an implicit internally, our implicit model gives us a Sine distance field representation of the geometry, right? We actually have full control over material inside or outside the boundary. And that allows us to do things like placement, to essentially move around material digitally to control where we want it to be, right? If we want it to be closer to the surface, we can do that. If we want it to be more inside, we can do that. And this ability to control material in a very efficient way is what allows this architecture to be better suited to this generation and the next generation of engineering problems. Additionally, it's not just about drawing these shapes, but it's like combining shapes to make new shapes, right? So all of the unions and intersections and all the operations, the low-level operations that you need to do on this model, they need to be reliable also. And when we're doing a Boolean union, right, in Sine distance field world, it's very simple. It's incredibly parallel. I think there's a better academic term for how parallel it is now. There's, ridiculously parallel. I haven't been following the latest papers to see what the cool academic term is for how parallel it is, but it's very parallel, the problem. When we're doing unions and intersections on a BREP, it's complicated. It's not, there's a lot of high branch divergence, right? There's a lot of different paths we can go down to calculate those intersections. And again, if we look at the way modern computers are built, right, with GPUs, et cetera, these parallel problems are better for the future of how we compute. And so because of that, right, with Sine distance field modeling, they work. Booleans are unreliable in BREP. So we can represent things or model things like a bone implant, these incredibly complex structures, essentially in real time. Oops, sorry. So that's the modeling core. The second part of this is field-driven design, right? With field-driven design, you can then tie the parameters of the implicit model that produces this Sine distance field representation of geometry. You can actually tie those parameters to fields. Now, a field, I think it's obvious to all of us, but sometimes when we're explaining this to people that are outside of the academic world or that are just in engineering, it's not always obvious, which is a field is just like anything in physics, anything in nature, right? If I was to go through this room and measure the amount of light at every single point, right, that would be changing, or measure temperature, or measure, if I was to hit my hand really hard, I actually have a stress fracture in my heel. So if I was to look at my heel, when I impacted it all the time running, there would be a certain amount of stress going into my heel, and that stress exceeded the maximum stress in my bone, so it cracked, right? And so fields are essentially the language of physics, the language of nature, the language of the world. It's the language that we as humans have used to understand the way the world works. We can now tie all of these parameters in our Sine distance field based implicit model to physics in the natural world. And that allows us to actually make a part that responds in a certain way to something. Like maybe you want holes to get, maybe you're designing the next generation speaker for the interior of a car and you want the hole pattern to like look really cool as it gets further back in the car because it looks like quote unquote fast. Or maybe you're making a bridge and you want the structure of the bridge to be really light and elegant and follow the stresses through the bridge. Or maybe you're making a bracket or a heat exchanger and you want the fluid to flow a certain way. We can do that with tying the fields from physics or multiple fields together to actually control the structures and patterns. So this is like a core, this is kind of the design method that this underlying architecture allows. And the field almost becomes a way or an abstraction on top of the Sine distance field model. So you can, as an engineer, start to build in engineering intent. Really simple example is you're making a turbine blade, right? You want there to be more holes in areas where there's higher curvature or more holes where there's less curvature because where the blade is shaped, the curvature is based on where the airflow is going over it. And you want the whole pattern to respond to that in a certain way. So it's getting cooler on the leading edge, less cool somewhere else. Again, this is very simple field-driven design application. Rocket nozzles are another good example. With a rocket nozzle, it's really interesting because, this rocket nozzle shoots fire out of it, right? There's flame. I should make a little GIF of fire shooting out of this. The nozzle gets so hot, it's hotter than any metal. Like these are like, the heat that the fire from the nozzle is producing would melt any material. There's no material that can withstand that. And so a good question is, how do these nozzles actually work, right? Why can we shoot a rocket up and it still works? The reason is we actually cool the nozzle. So like in between the edges of the nozzle, there's other types of nozzles that actually do burn up, but I'm not going to talk about those. They're called ablative nozzles. These nozzles, they're called regen. They're regeneratively cooled. So the fuel, which is very cold material, is actually pumped to the bottom of the nozzle. Oh, you guys can't see what I'm pointing to. The fuel is actually pumped to the bottom of the nozzle, and then it goes up through these cooling channels to cool the metal so it doesn't melt away. And then it goes into the engine at the perfect temperature for combustion because you don't want to combust too cold of a fuel. And this is how we can make reusable rocket nozzles, by cooling the nozzle. You can drive the cooling channels. You can make if you can make more efficient cooling channels, you can make the nozzle itself lighter. You can make it perform at higher pressures, et cetera. And so again, you can use the fields around stress, around thermal properties to drive where these cooling channels are. Chips, et cetera. This is a video, let's see if it plays, just to show the kind of real-time interactivity. So like as you're changing the parameters, one of the important things is to be able to actually see these parameters update in almost real time. And so if you have a model that doesn't break, it's great. But if you're still waiting a really long time for it to update, that's a problem. And these happen to be stiffening ribs on a casing for an engine. And so again, these are making some changes to the parameters, and it should update relatively quickly. So this is in our software. I'll at the end talk about this. Yeah, so again, like being able to push on the model and play with it and experiment with it. One of the things to note is these Sine distance fields are new to engineers. There's some differences to working with a Sine distance field than a BREP, right? The actual topology of the model is built differently. We don't have edges and surfaces to click on. We have design parameters that control functions in the model. And so being able to move these and change these, like could be a blending parameter, it could be a thickness parameter. This happens to be a heat exchanger for a chip. Additionally, this is a prosthetic. So yeah, again, you can see these different parameters that you're adjusting in the model. You want to see how they respond in the model. on anything, even like things like these gigatype lattices where you have gigantic structures with billions of cells. Which is a note. So the reason that our company is called nTopology, nTop, the idea is any topology. Literally, you should be able to, like, topology is how we describe shapes. We should be able to model any shape with the software. That's kind of what we set out to do. All right, let's see, this is almost done. And again, you can see the field-driven design applied here where the structure is getting a little more dense or thicker. Okay, where are we making an impact? What industries? So, excuse me, essentially anywhere where products are made, right? If you look around, pretty much everything has been designed in the computer. It's been designed in one of 4 systems based on the same underlying technology. We're now embedded across all of the major engineering industries. Well, did someone interrupt me? No. Cool. Aerospace and defense, automotive, medical device, and consumer products. And my recommendation also for anybody who's working on research in these areas is really find people in the mechanical engineering department who are designing products and talk to them about the problems they're having. Reach out to them. Go have lunch on the steps of the mechanical engineering buildings and say, hey, what are you guys working on? I think it's really important to be close to the day-to-day problems that engineers are working on, whether it's trying to do the design of a iPhone case or a chip heat exchanger or a medical implant or like the structure of a car or rocket nozzles. Like, what are the problems they're facing? And talk to them about that. The stuff we found, right? Architected materials. So this is a CubeSat structure that the US Air Force designed in our software. It's one of the first products that flew from our software. The idea here was they wanted to turn around the design of a more efficient satellite as fast as possible. And they came up with the structure that's kind of, I like to say it's like making corrugated cardboard, but out of metal, right? Corrugated cardboard is really light and it's really strong. It's light and strong because the material's in the right place. And so here they're using a material that actually happens to be very dense. It's a nickel superalloy Inconel. And Inconel is normally way too dense to like fly into space. But because they're basically converting it to corrugated cardboard, this structure is actually as thin as about 3.5 human hairs. And it's basically optimized to withstand the takeoff vibrations. Like the whole thing is vibrating when it takes off. They were able to make this actually in Inconel 50% lighter than the original design in aluminum, which is kind of profound because Inconel is actually a lot more dense than aluminum. A lot of applications initially in advanced manufacturing, right? And so, we're not going to market initially replacing CAD, right? CAD is a good drawing tool. It's solving 95% of the problems that exist today. We've entered the market kind of solving the 5% of the engineering problems that are around advanced manufacturing. And this new application space opened up by advanced manufacturing is where we're targeting. And that is a growing space, which is really exciting. But advanced manufacturing, things like automatically generating tooling for structures, designing structures that are, 5-axis machined, customizing. Some of the stuff is like, quote unquote, like boring factory floor stuff where advanced manufacturing is used in the production of parts, even though like the end use part is not built. So like, again, this bottle, it's not 3D printed. However, in the production process, there was most likely 3D printed tooling. There is most likely some jigs and fixtures to support the part as it comes off the line to measure it. The value chain of engineering and products is really massive. And again, another piece of advice would be like talking to mechanical engineers and seeing what are the problems they're facing. It might not just be like the design of the bottle, it might be the design of the whole production process of that bottle to make it more efficient. And then there's kind of the, let's say, there is the design side too, right? The consumer product design. There's an aesthetic developing around these advanced manufactured structures. You know, you see it with Adidas and the shoes that they released, Rydell with the helmet. These are structures, you know, foam, designing foams, designing seats, because you can control you could essentially now with 3D printing, you're controlling the material properties of your part locally throughout the part. So you can say, hey, let's make it a little bit stiffer here. Let's make it a little bit more flexible here. So you can make a seat that's more comfortable for somebody who's like in the Tour de France and is on that bike at high speed for a long time. Right, then there's the beauty of these structures. I mean, let's face it, we also are all excited about how beautiful these structures are. Like again, I think there's a natural drive as an engineer to try and make things, not just copy nature, but actually make things better than nature. And then the nasal swab design as well for COVID. So this was kind of an exciting one. The customer was able to explore, like, you know, in 2 weeks, 100,000 different nasal swab designs, print and test the top 100 of them, and get a nasal swab FDA qualified for use within like 2 weeks, which normally this would have taken months. A little more detailed case study. So with heat exchangers, so this is a heat exchanger. It's a fuel cooled oil heat exchanger. So the fuel pulls the heat from the oil going through the heat exchanger. And again, we have massive volume reduction. So the gray is the old heat exchanger that was built manually with like tubes that are, that are literally brazed together. They hand build these heat exchangers. It's crazy, essentially, and braze them, which is like big soldering. And those braze joints between all the tubes, they crack and break. And so the heat exchangers have to be replaced a lot. If you have to replace the heat exchanger, it means the aircraft can't fly. They have to get another one coming in. The 3D printed ones can handle more pressure. And they're more efficient and they're smaller. And also, if you need to replace them, you don't have like one factory where there's like a guy sitting there who's like a specialist at brazing, putting it together. You just have your 3D printer build them. Medical implants. So the medical device industry has gone through a massive revolution in the last 5 years with 3D printing, in that they're building these medical implants. They call them quote unquote glueless implants. So it's a medical implant that they used to like take a medical implant and they would like slather some glue on it and put it in your body, and your bone would be glued to the implant. And then 7 years later, they'd have to go back in, take it out and replace it or re-glue it to put it back on. Now these medical implants, they're called glueless because they don't need glue, and they don't need glue because literally the implant is designed so that the bone grows into the implant and fuses with the metal. The one downside is that these are only good to be implanted into people whose bone is still growing. So if you have osteoporosis, if you have a degenerative bone disease, these don't work. So that's one issue with these. So they're not like the end all be all savior for bone implants, but for a group of people that these do work well with, these are phenomenal because they essentially last forever because the bone fuses with the metal. And consumer product design. We have a number of companies releasing new digital product lines where they're, again, tuning the cushioning of a shoe, tuning the cushioning of a seat, etc. Some engine cases, and I'll jump into some of the challenges and unknowns. So a couple of challenges. So first off, because nTop is a new mod, like because we're based on this new architecture, we're not like this full end-to-end 40-year-old CAD suite that can do everything, right? We still need to, we don't have the assembly in nTop. The assembly is still in CATIA or NX, right? The assembly being like the whole phone. Like if they're just doing the chassis of the phone in nTop, that chassis still needs to go back into the whole phone model that's digitally captured in CATIA or NX. And so that means nTop still needs to connect with traditional CAD system. And there's a number of ways, like the The worst way to do it is take the implicit and actually have to tessellate it or come up with the boundary, a BREP from the implicit, and then just put that BREP back in the CAD system. There's other smarter ways that this can be done, whether it's, having the implicit rendered with the CAD model, having a BREP that represents just a boundary, a dumb kind of body, but has properties associated with it. But there's a whole realm of problems in terms of incorporating nTop with traditional CAD, right? Like one pipeline we have, which is a little insane, is, generate the part, tessellate it, come up with a BREP, come up with surfaces, and then bring those surfaces back into CAD. There's the other side of the problem, which we don't think about as much, but I think this is also a big open space going forward. Like if we think about Sine distance fields becoming a new standard for engineering, being able to take the old CAD models that exist, analyze their own feature tree, and then generate an implicit from that so that we can have both ways compatibility. That's a fairly big open area. I do think we're still going to need to create meshes for a long time from these implicits. This is a hard thing to do. It's it's hard to create something that's both manifold, watertight, has sharp features on every single design possible. We have a great database of like really, really hard models. So if anybody is working on these problems and wants access to some of these, like we found in almost every paper that we've implemented, we found models that won't work through that. So this is still it's still a hard space. I don't know if it's as exciting from academics because it's like 90%, 95% there, but it still is something that, for our customers, this is something that they still struggle with. And then creating the CAD models from these implicits, also preserving the analytical surfaces while keeping the organic surfaces, right? Like in CAD, you want to know that that's a circle. You want to know that that's a cylinder. You also want to know that that's some smooth surface and where points are on that surface. So that's important. Computing Sine distance fields is also another area still, like, some of the equations we have are not true Sine distance functions, right? Like especially with offsets, and there's a lot of surprises that you can run into when you start working with Sine distance fields because you're representing like all of space with these equations, and so even if we're just rendering the surface, right? We're not rendering all of the whole 3D space, and so if there's like some weird thing happening in your field far away from the surface, you as an engineer might not know that. And then when you try and offset, all of a sudden you have like weird bumps or some mystery that's confusing. And so, whether it's taking something that's not a Sine distance field and then, trying to rationalize it so it is a accurate Sine distance field, that's something that's pretty hard. And especially it's hard because we need to do it in real time, right? Like if you make a change to the model, you need to update that immediately. A good example of that is like just with these gyroids are used for heat exchangers a lot because they separate space into multiple domains. And the simple equation, the cosine based equations, they don't give you an accurate distance field. So the wall thickness of those is actually not easy to calculate and easy to compute in real time. Because again, engineers, it's like really cool that the math works to give you this funky looking shape, but the engineer wants to know what the wall thickness is throughout here, right? Like when we're engineering with these, we need to know precise dimensions. And it's fine if they're within tolerance, but we need to know what that tolerance is. We don't need to be perfect as engineers. That's one of the nice things about engineering compared to mathematics is we don't need perfection. We just need to know within what the tolerance is, and we need to be within that tolerance. And so I'm okay with knowing that our wall thickness is this thickness within this tolerance, but we need to do that. I'm not okay with like taking my ellipse and offsetting it, and all of a sudden my ellipse is not uniform wall thickness throughout. Another space that's really interesting and exciting is traditional manufacturing from Sine distance fields. So we tend to focus on 3D printing just because there's a lot of new applications there. Customers are willing to adopt new software in that area, but there's a lot of opportunity in CNC machining, injection molding, casting. And so like computing the tool paths from sine distance fields, coming up with a machining workflow that's based on sine distance field architecture. I think this is going to have a ton of value in the industry going forward. And so this is something, we as a company may even sponsor some research for this, for example, because I think it presents a big opportunity. Another manufacturing. So with that said, just to kind of summarize, right? We're built on top of a new architecture. That new architecture is useful for a lot of these new applications that are coming up because of the shift in manufacturing. This new architecture is new, it's different. There's a lot of stuff we still need to build on top of it. And there's a lot of research that's needed to make this a real industry. But the exciting thing is, we're at the tip of the iceberg today. We have real products on the market that are built on top of this sine distance field modeling tech. And the product is more or less there. And so I think again, it's early days. And I think for all of you, it's probably the most exciting time to be in the field, because when I started the company, there was no software there was no software that could do these type of parts that were starting to make structures that are actually performing better than structures that you would find in the natural world. And now we can do that. But in order to really industrialize this as an industry, we need a lot of it. It takes a lot of collaboration between the research side and the business side and the customers. I think it's very important, as I was saying earlier on, to really focus on the problems that the customers are having. And that customer, if you're in university doing research, might be somebody from a company that you're talking to, or it might be somebody from mechanical engineering, or it might be your buddy who's working at Honda, who's designing these products and getting close to those problems. And so with that said, I really appreciate the opportunity to talk here. Hopefully this was informative in some way. I have two plugs. One, our software is free for students. So if you have your friends that you're making on the steps of the mechanical engineering department, you can recommend them to get our software because it's free for them. And two, if you're interested in collaborating with us, reach out to us. We're very open to collaboration. We work really closely with universities from NYU, Carnegie Mellon, DTU, University of Colorado Boulder. We're open. We're really open in working with research because we know how important it is. We're not going to be successful in creating the next generation of engineering software without all of you. So appreciate that. And I love working with you guys. So thank you for that. And Keenan, thanks for having me here. It's always awkward, the claps when you're doing. Yeah, exactly.
That's roaring applause. Yeah.
Nice.
Great. So thanks for this great talk, and definitely inspiring talk in terms of lots of research questions, lots of open questions to answer. We've had a lot of activity in the chat actually of people, thinking about, okay, how well does this really work? What are the problems? And so we have plenty of time for questions here. I wanted to just first kind of one question and comment based on something you said. You were talking about these implicit surfaces and extracting meshes from them and how that's still a challenge for you. And this ties into, you probably didn't see our opening ceremony, but one thing I mentioned is that a really, really great way for companies and different people who want to get researchers thinking about a certain problem interested is to release a data set. Because I think a lot of people in the research community would look at that question of extracting isosurfaces from implicit functions and say, yeah, that's pretty well solved. And to have a real data set with real interesting problem cases is going to really help people understand what are still the issues. Why is it that, what we believe is the solution is still maybe not really the solution for people?
You know what? I think that's a great idea, because additionally, the data set's there's always up leveling, right? If we're using the data set of CAD models, for example, the data set that I've seen from Onshape, right? Those are only going to be a certain complexity because they're on the order of complexity that BREPs can represent from the beginning. But we should release a sine distance field data set of the next generation of really, really, really hard stuff. And let's see.
I look forward to seeing that at SGP 2022.
Yeah, so let's do that.
Okay, great. Okay, so then I'll take it to the audience for questions. And maybe I'll start by just kind of recapping some of the questions in the chat. So Albert Tono said, as a previous architect, how would you envision nTopology in the AEC industry, especially in the ability to control the interior spaces? I don't know what AEC is, but maybe you do.
Architecture, engineering, construction. I'm glad somebody asked that because, like, you know, it's just kind of a funny story, but when I was in architecture school, like I got into this because of working with 3D printing in architecture school. And like early on, I always was like, okay, these 3D printers are going to have a major impact in the way we make things. The way I know how to make things is in the building industry. But you know, when I graduated, I was like, wait, but 3D printers are so small. We're not going to 3D print like models of buildings, like Zoolander models, right? Like it's not going to happen. We're mechanical engineers make products that are on the scale of what 3D printers make sense. So that's kind of how my career direction ended up in mechanical engineering more so. But I think it's always been an interest to look at the building industry and see what's possible. I think it's going to have implications in the building structures that we design initially and like the tooling and fabrication process of buildings, just because you see these like large kind of like, I don't want to say dumb because they're not dumb, but they're like, you know, fairly simplistic 3D printers that are like big, giant, like machines that squirt concrete. And you can only do so much from a shape standpoint, but you can start building structures with that, or you can 3D print tooling on these big machines for the structures to be built. There's probably applications in the design with based on like a SDF technology where you're doing the layout of buildings really efficiently and quickly. So you can like anything where you want to do a big study of how parts change and shift based on tuning that. So like you could think of like an office layout and moving stuff around. That might be good for a modeling tech like this. I realized one area I didn't put at the end was like on the advanced simulation side of things, like tying more advanced simulation on top of these models. I think that's actually one of the most interesting areas of research going forward, is like having a pure simulation pipeline that's mesh free. So you can do analysis directly on top of the sine distance field models. And then getting rid of meshes completely. Some of these problems are like problems we're facing today, and I wasn't thinking like big picture enough. So that's something to note. And if anybody out there is working on that, like we want to talk to you.
Yeah, actually, the next question is very much along that line. So it says from Honorio Samaron, how does this framework integrate into complete design simulation and lifecycle product management pipeline, which is often fully contained in already established packages? And so maybe, you know, also to kind of to build on that, you know, can you say a little bit about what you do right now if somebody wants to do analysis on these models?
Yeah, so to do analysis on these models, we come up with we tessellate the boundary, and then we build a 3D mesh from that boundary, which you feed into the analysis pipeline, which is like the dumbest way possible. It's like we have this beautiful, lightweight, you know, kilobyte size representation that we could render and do analysis on. We could render and visualize in real time, and then to solve all the physics, we need to like tessellate it and go back to a BREP essentially, is like ridiculous to me. Now, there's a good reason for it, which is our customers are very comfortable with their simulation tools. Their simulation tools are based on BREPs and meshes and 3D meshes, volumetric meshes. And so because of that, we kind of needed to do that first, because that gives them the comfort that like the designs that because at the end of the day, the customer doesn't really care if it's a sine distance field or a BREP or whatever. They care that they could get the design that they want or the product that they want as quick as possible. And so what they like, I used to go to customer sites, like we could have like long conversations about starting the company and stuff like that, but I used to go to customer sites and talk all about like sine distance fields and like the tech, and the customers would look at me and be like, okay, cool, sounds like you're smart, but so what? So I don't know what that side track was about for a second, but like back to simulation, right? The customer wants to run an analysis on their part. They need to run an analysis on their part. And so they don't care that it's sine distance field or BREP. We do, because we know that the sine distance field core is going to allow them to get that quicker and faster. but we needed to integrate with their legacy analysis packages. So and we have plugins for these tools also. So you can in nTop today, you can do the pre-processing of your physics model, send that to ANSYS, run the analysis, pull the field back. The cool thing, the advantage is you can take the field, the data from the results, and actually tie that back into the design, which is normally done manually today. The other side of things is we have our own analysis in nTop too. So, but again, for our own analysis, it's also traditional FEA run on tetrahedral meshes or volumetric meshes, and solving for linear static stress analysis or thermal. We do transient thermal, which is kind of cool, but it's still based on traditional meshing tech. This becomes very powerful. If we could remove meshes from that pipeline, this becomes a real-time, imagine being able to design with all of the analysis in real time and push on your model and immediately see, oh, if I move it if I adjust this design parameter for surface thickness, all of a sudden my stresses come way down, but my volume is going up, and you can see that in real time. It's I don't see nTop being just this hidden thing that's a black box that you just push a button and get a part. It's really a combination between you as an engineer driving the model, and to do that you need this real-time feedback. And the analysis is a very big bottleneck that if we can do real-time analysis on something more resembling a signed distance field, we're in a good position. I mean, voxels are one step better because it's quicker to calculate, but that's still not good enough.
Great. So fortunately, right now you're in a room with a bunch of people who do care about the signed distance field.
Yes, good.
And want to know more about the details. So we had a lot of questions with people saying, okay, well, first of all, are these really signed distance functions, or are they things that don't quite have the signed distance property? If so, how do you convert it back into a signed distance function? How do you do how do you deal with the fact that booleans of signed distance functions don't give you signed distance functions, and so on? Maybe can you just talk a little bit more about the kind of technical issues and solutions you run into with SDFs?
Yeah. So one of the main things is we actually don't. I said signed distance field at the top, but we actually call it an implicit model because we don't have a true signed distance field the whole time, and we're okay with that because there's certain things we can do when we remove the constraint of it having to be a signed distance field that actually can do some really good engineering things, like calculating mid surfaces between two parts and figuring out where there's midpoints and having lots of things repeated and things like that. Again, there's very dumb, simple solutions. So if we want to recalculate a signed distance field from a design that we have that gives us a nice boundary that we mesh it and we recalculate the distance from the mesh. And so that's obviously not the answer that anybody in here wants to hear. But if somebody has a better way that's efficient, we want to talk to them. What we do with the way the model is constructed is essentially, it's constructed as a big function, and we could analyze and understand different parts of the function. For more details, I would have a separate conversation with the tech team. If you want to email me, we can talk about that. But it's essentially we solve different parts of the equation in different areas at different times, and build that from there.
Great. Okay, so
there's good open source tech around signed distance field modeling out there that you can build on top of.
Excellent. Okay, so now I will open up the floor to anybody who has other questions that we haven't covered yet. So please go ahead and.
By the way, the chat, I'm saving the chat because I think there's some really interesting stuff that's come up in the chat.
Yeah, actually, while I'm waiting for more questions, I'll ask one more that showed up in chat. So main concern when producing software for big mechanical manufacturers like turbo machinery is that they like being able to get back and edit the original design, introduce their own user-defined features, and compare with a fabricated version to locate manufacturing deviations. So is that a process that kind of shows up in nTop's platform?
It's a process that our customers run into. By the way, this link that you just posted on the distance functions is really a good one. That's a good resource if you're just getting involved in this. Also, there's a person who works for us, Johan Korndorfer Coupe. He has a good site as well, which I can find and post here. In terms of the concern about looking at user-defined features and fabricated versions and looking at issues, this is actually a nice one, because what happens is for the new generation of parts, they'll do a CT scan of the part, and you can actually bring the CT scan in, reconstruct the surface from it, and look at deviations that way throughout. Like, you're essentially like the core problem, I think, or the core issue is like, when do you discretize the sign distance field, and how could you discretize efficiently and in a nice way, right? Like, your sign distance field is like perfect, or your math equation, your equation-based implicit model gives you the perfect 3D definition. But when and where you discretize that can give you more information that's useful to engineers, right? Like if two surfaces match. So if you're discretizing over slices, you can start to look at pixels and do some analysis like that. The pipeline for part analysis, the other way people do analysis is by tapping a part. So they fixture it in a way and they check certain points that are important on that part. And so you can place points on the surface of your implicit that are your touch points, and then you can see how those match in the real world. And that's a nice thing. But these, again, this is like a good thesis project for somebody to come up with, like, look at the analysis value chain. How do you do analysis, you know, the valid V&V or validation and verification of parts. Yep.
So I'll ask one other question, which is that you all have been using sign distance functions and implicit functions for quite a while now, but just recently in computer vision and geometry processing and graphics, sign distance functions and other implicit representations have kind of had a renaissance for learning and acquisition. And so I don't know, you know, there's been tons of papers on neural SDFs and all this kind of thing. Is this something that nTopology is keeping an eye on and seeing connections between the engineering work and what's going on in these communities?
Like 100%. I think, like, again, I didn't put that in the next generation problems because I was kind of thinking like, what's locally, like, what are we solving today, which was probably a missed opportunity. But I think that the AI future of this is like really, we can't, like, to do AI on top of a fragile BREP model, like, doesn't make sense, because we need to change parameters, the data sets we can't generate quick enough, fast enough, artificial data sets, et cetera. And so we're keeping an eye on this, on us. And I think it's early still to be, like, I haven't found a good problem yet that it's really solving, but I think this is something that's, like, I think the implications are really interesting when it's like, okay, if once you give an engineer the ability to tune parameters and see how the model updates and changes based on that, then the obvious next question is, which parameter should I change if there's 10,000 parameters in this model, right? Like, and so I think AI is going to be able to solve that, but I think that's like one level deeper than where we're at today.
Great. Okay, I'll ask one more question here.
Sorry, I'm so excited looking through the chat also.
Yeah. So I'll ask one more question from the chat here. Emily Yu says, implicit representations are becoming popular for early stages of the design process, like for shape design and ideation stage, or for purely artistic design workflows. It seems like this is a pretty interesting way for designers to create shapes from scratch. Do you plan to explore these use cases at nTopology? So I guess for the ideation stage rather than the engineering.
Yeah, concept design. I think it's something I'm fascinated in. We definitely watch Magica CSG because it's like a fun, like, we play around with it because it's a fun software to use. If anybody knows the person who creates Magica CSG, we have this. So I think one of the things that's going to be interesting in the industry is a format for trading implicits around that's lightweight and easy. We've built one called code reps that we're working on, and the code rep essentially is just a way of capturing the implicit model and being able to share that. And you, as the receiver of this code rep, are responsible for rendering it and doing operations on it and solving it essentially. And we think that as a a format for interacting between programs could help build the industry more so. And so, you know, Magica is a fun tool to use. I would love to be able to see somebody do like some sketch in Magica, bring it into nTop and like do some engineering work with it. Dreams I haven't played around with, but I've seen videos of, and it looks really cool too. But as far as I know, it's a video game.
Okay, terrific. So unless we have more questions, I guess we'll thank Brad again for this very thought-provoking talk. And we will start back again at, well, in local Toronto time, it's 12:40 for the next paper session. So see you later.
Keenan, thank you so much for having me. Alec, it was a pleasure. Hopefully that this country will open the border soon and you'll be able to come and visit, or I'll come over there.
Yeah, you're very welcome to.
And for anybody in the room, if you guys are in New York City, when I'm there, please reach out, shoot us an email. My email address is brad@nTopology.com. It's very easy. And I'd love to grab a coffee with you, invite you to our office. You can meet some people on the team, etc. Hit us up. Yes, Sylvia, if you come, let me know and I will wait in line for Hamilton tickets. I'll do that. So enjoy. Thank you guys for having me. This was a pleasure. Appreciate it. And I hopefully next year in real life, right? So
okay. Awesome.
All right. Thanks again. Bye-bye.